Okay, so we're going to follow this second path here. Okay, and so in order to do that, we need to learn a little bit more about operators. We've introduced them a few lectures ago, but we need to learn a little bit more about them. And so, generally speaking, we can define an operator to be a function which acts on a function or functions to give a new function or functions. Okay, so there's a lot of functions there. So it's a function that acts on another function or functions to give a new function or functions. Okay, and so a simple operator would be just multiplying by x. So x times f, so if we multiply f of x, our function, by x, then we can define, and we basically can define the operator x hat, and the hat just indicates it's an operator, equal to x. That is, you multiply by x. We can define an operator as the derivative. So if we take the derivative of f of x, then the operator would be just the derivative in time, for example. Okay. Now this hat notation can just get a little bit cumbersome, and so sometimes I'll use it, sometimes I'll drop it. Just remember, usually it's kind of obvious from context whether I mean an actual variable or actually mean an operator. Okay. So in quantum physics, every physical quantity has an operator that's associated with it that acts on a wave function or wave functions. Okay, and so anything that can be measured has an operator. Okay, so we've already seen some of these. So if we imagine that we have a plane wave solution, so a wave function. Okay, this is not what we'd find. We would not find a plane wave in the solution for the harmonic oscillator, but it's kind of a generic wave function. Then if we look at the operator, if we look at the quantity IH bar d psi dt, where again psi is this plane wave solution, then if you take the time derivative of psi, you get plus h bar omega when you multiply by IH bar, and so h bar omega is equal to E, right? Energy is equal to h bar omega. That's one of the de Broglie relationships. And so in the end, what we have is that our energy operator is equal to IH bar d by dt. Okay, and that's the total energy. If we have if we take minus IH bar derivative of psi with respect to x, then again when we take the derivative of psi, we get h bar k times psi right back. Remember, the derivative of an exponential is just an exponential times the derivative of the argument. Okay, so we multiply by minus IH bar. We multiply it minus IH bar times ik, and we get h bar k times psi. And so h bar k, we know it's another de Broglie relationship, is equal to p. Okay, and is the momentum. And so the momentum operator is equal to minus IH bar d by dx. We've already talked about that one. And we've already talked about this one too, minus h bar squared over 2m d squared psi dx squared, which is equal to the kinetic energy. So this is the kinetic energy operator. Okay. So now with we can write the Hamiltonian operator. Okay. The Hamiltonian operator is defined to be the kinetic energy operator plus potential energy operator. So it's just minus h bar squared d squared over 2m d squared dx squared plus u of x. And so with this Hamiltonian operator, for the time independent case, we can write that the Hamiltonian operator operating on psi gives us the energy, which is a number, times psi, because the energy is the kinetic energy plus the potential energy. Okay, and so this, as we've kind of already indicated, this general form of this equation is known as an eigenvalue problem. Basically what you do is you ask, what are the functions psi sub n and the values, generically lambda sub n, such that for a generic operator q, we have an equation that satisfies this relationship. That is, the operator q acting on an eigenfunction gives you the eigenvalue times the eigenfunction right back. Okay, so